So hi everyone, thank you for coming. Today we have Hyerin Cho from Harvard, and she will present her work and her numerical simulations on black hole accretion and feedback. So please go ahead.
Good. Thank you so much for inviting me. I am Hyerin Cho. I'm a finishing PhD student at Harvard University, working with Ramesh Narayan and wonderful collaborators. And today I'll be talking about bridging scales in black hole accretion and feedback based on these listed papers. Okay. So we now believe that supermassive black holes and their host galaxies constantly talk to each other via accretion and feedback, and there are many observational evidences. First, we have correlated properties between black holes and their host galaxies, where the most famous example being the M sigma relations shown here. Galactic star formation and black hole accretion rate, they share similar histories as well. There are direct observations of AGN feedback in the form of jets or winds, and from the fact that AGN feedback can solve many problems in galaxy evolution, such as the cooling flow problem. Theoretically, accretion and feedback has also been widely studied. For accretion, the simplest model of accretion is the Bondi accretion, of course, where the gas accretes onto the black hole in a spherically symmetric way. In this model, the important characteristic length is the Bondi radius, the radius within which the gravity of the black hole begins to dominate. For feedback, Blanford's Naive mechanism is important in astrophysics. In this mechanism, simply put, the general relativistic frame dragging effect of the spinning black hole spacetime drags around the magnetic fields around it and winds up the magnetic fields, which ends up in a powerful relativistic outflow. Even if the topic of black hole accretion and feedback is a widely studied topic in both observational and theoretical fronts, there are still remaining questions. And the questions that I'm interested in addressing are how much of the gas from the galaxy actually reaches black holes? And in return, how much of the energy does the black hole deposit back onto the galactic scales? The bidirectional communication between black holes and galaxies is remarkable when you consider the vast dynamic range associated with it. In the scale bar, I'm showing black hole-related scales on the left and galaxy-related scales on the right, where the x-axis shows the radial distance from the black hole in terms of in units of gravitation radius, RG. If you're not familiar with RG, this is just half of the shorter radius, which depends on the black hole mass. On the top x-axis, I've also converted that to physical units in kiloparsecs for M87's case. The Bondi radius is typically around 10 to the 5 Rg to 10 to the 6 Rg. So I've shown that as a vertical dashed bar here. As you can see, the scale difference between the black hole and the galaxy spans over 8-9 orders of magnitude. And because of this very vast dynamic range, simulators have typically divided this huge problem into two different regimes and have studied each regime separately. The first method is to use galaxy simulations or cosmological simulations using Newtonian gravity. And they typically cover this part of the scale bar. While these simulations are successfully reproduce realistic galactic environments, the resolution near the black holes are not sufficient to fully track self-consistently the black hole accretion and feedback. As a result, they need ad hoc subgrid prescriptions to model these missing processes. On the other extreme, there are GRMHD simulations, which stands for General Relativistic Magnetohydrodynamic Simulations. These simulations solve general relativistic equations at sub-horizon resolutions, and therefore can track self-consistently the black hole accretion and feedback. However, these simulations are very computationally expensive and therefore can only reach steady states up to maybe 100 Rg. As you can see, there is a large gap in scales where either of these simulations cover, and this has been the main challenge in understanding how black holes and galaxies have interacted with each other. So what's stopping us from constructing a very huge simulation, which covers also the galactic scales, but also resolving black hole scales, and just wait long enough to converge? The fundamental problem limiting these simulations are a time-stepping issue, which I'll describe in this slide. So again, imagine a hypothetical simulation that has that simulates the large galactic scales, but also resolve the small black hole scales. If you have this simulation, the time step of the simulation will be determined by the smallest scale, which in this case is the black hole horizon scales. This is because of two things. One, the current condition for numerical stability of the simulation, and second, because the gas dynamics are dominated by the energetic processes in the vicinity of the black hole. On the other hand, the total runtime of this hypothetical simulation will be determined by your largest scale. This is because larger length scale often involves longer time scales. For example, the free fall time scales as r to the 3/2, meaning that your largest length scale will take a longer time to evolve. So in this case of a simulation with a vast dynamic range in length scale, directly translates to a very big difference between the time step and the total runtime of your simulation, which leads to a very computationally expensive simulation. To give you an idea, if you want your simulations to converge all the way from the event horizon to the Bondi radius, typical GRMHD simulation with a moderate resolution will take you up more than 100 years to complete the simulation, which is very impractical. However, there has been significant advances in this field of bridging scales between black holes and galaxies. The first two methods I'm describing here are zoom-in simulation methods, depending on whether you're working with the grid-based code or particle-based code. Here, the idea is to begin with the large-scale coarse resolution simulation and progressively enhance your resolution over time until you reach the black hole related scales. Using this method, they were able to successfully track the accretion from large galactic scales all the way to small black hole scales. However, by the time they reached the high resolution phase in their simulation, they were again subject to the time-stepping issue, the critical time-stepping issue that I've described before, and therefore could not track the other way of information flow, which is feedback from small black hole to large galactic scales. The third method is to basically wait until your GRMHD simulations converge to larger and larger dynamic range. But as I demonstrated before, this is almost impossible to do so with a realistic scale separation between the black hole and galaxy. So their approach was to artificially reduce the dynamic range by making the Bondi radius smaller, much smaller than realistic value, or equivalently increasing the gas ambient temperature to a much higher value. By doing so, these approaches were able to track both accretion and feedback self-consistently. However, since they had to reduce the dynamic range, they could not fully connect the true scale separation between the black hole and the galaxy. So we wanted to tick all three boxes, or in other words, track both accretion and feedback over realistic sizes between realistic size differences between black holes and galaxies. And therefore, we came up with a new simulation method that we call the multizone method to fully bridge these very different scales for the first time. In this work, we use a GRMHD code called karma, which are designed for hot accretion flows or radiative inefficient flows. So typically, the computational cost comes from simulating highest resolution small scale cells. So the core idea of this method is to not evolve the small scale cells all the time, but only intermittently. Instead of jumping into the nitty-gritty details of the method, I'll show you how this method works by showing one of our simulations movies. Here in this plot or movie, I am showing the black hole in the center, and the largest radius extends beyond 8 orders of magnitude larger than the event horizon. Because I'm dealing with a vast dynamic range in length scales, I had to rescale the radius in logarithmic scales to show you the full dynamic range. When I play this movie, you will see that this black circle moves in and out multiple times, and anything inside this black circle will stay frozen. This is a key step of this method. By not evolving anything inside this, any small scales inside this black circle, we are avoiding the critical time stepping problem and relax the time step for larger scales to react to any feedback from small scales. When I play this movie, when the black circle moves inside the event horizon, the gas finally accretes onto the black hole, and the Blandford-Znaic jet is self-consistently generated from general relativistic effect. And when the black circle moves out, any small scales inside the black circle stays frozen, and that allows the time step to relax, and therefore the jet can propagate out to galactic scales. We repeat these V cycles over hundreds of times, and the goal here is to obtain a quasi-steady state of black hole accretion and feedback over a wide dynamic range. The true power of this method is shown in this plot. The y-axis shows the computational cost, or in this x-axis, I'm showing how many human days needed to evolve one free-fall time scale at the Bondi radius. The x-axis shows the dynamic range parameterized by the Bondi radius in units of the gravitation radius units. As opposed to conventional GRMHD simulations, which are shown as black dots, where the computational cost increases very steeply with increasing dynamic range, you can see that both of our multizone methods, shown in green and blue, have a very flat curve, meaning that when you want to simulate a larger and larger dynamic range, you only need to pay a modest cost in computation. In actual numbers, for a realistic value of the Bondi radius, while conventional simulations will take more than 100 years, the current version of the multizone method, we can achieve the same goal within half a day, which is around 10 to the 5 times speed up. Okay, so since this kind of simulation has never been done before in astrophysics, we wanted to make sure that this method produces reliable results. So we carried out several different tests to validate the method. And our approach here was to begin with the simplest case possible, and then add one complication at a time to test this method. Of course, the simplest problem to test it is the purely hydrodynamic Bondi accretion case with black hole spin of 0. This problem is especially good because there exist general relativistic analytical solutions available. And when we simulated this problem with our multizone method, we found a perfect agreement with analytical solutions without any feedback. Now, when we add magnetic fields, we knew that there will be turbulence and also inflow and outflow together. Since there exist no analytical solutions that we can compare our solutions to in this case, our approach was reduce the dynamic range of our multizone simulations such that so that Bondi radius is around 400 Rg, where conventional GRMHD simulations can also handle. The problem is small enough so that conventional simulations can handle as well. When we ran these sets of simulations, both in conventional methods and our multizone method, we found a great agreement between these two simulations and confirmed that this produces reliable time average results. Now, after all these tests, the core idea of the multizone method is now beginning to be used in other research groups, such as the Princeton group and the Caltech group, which really represents that we have come up with, we are now in the regime of simulating very large dynamic range. The simulation method, multizone method, enables simulations like this. Here I'm showing one simulation snapshot where the Bondi radius is with a realistic value and a black hole spin is 0.9. Top rows show temperature and bottom rows show density, both zooming out from left to right. And you can see the relevant scales in a scale bar on the left bottom corner. The relativistic jet, which can be identified as high temperature and low density regions, is self-consistently generated near the event horizon and is propagated out beyond the Bondi radius shown as dashed circle here, and even beyond a few times the Bondi radius shown as dotted circle, where we're now entering kiloparsec regimes all the way from event horizon scales. This is now for a single simulations, but this year we were able to complete a full library of simulations ranging with Bondi radius ranging from 400 Rg to 10 to the 2 times 10 to the 6, with black hole spin ranging from 0 to 0.9. And with this suite of multi-zone simulations, we are able to extract important information about accretion and feedback. So what have we learned from the simulations? For accretion rate, here I will separate out only the black holes, non-spinning black hole cases and see how the accretion rate changes as a function of Bondi radius. So here in the y-axis, I'm showing the accretion rate in units of the Bondi accretion rate, and the x-axis shows the Bondi radius in units of the gravitation radius. When the Bondi radius is expressed in terms of the gravitation radius units, you can see that it's only a function of T infinity, which is the temperature beyond the Bondi radius. So I'm also showing T infinity on the top x-axis. The horizontal bar, gray bar, shows when the accretion rate is exactly equal to the Bondi accretion rate. And anything below it means that the accretion rate is suppressed with respect to the Bondi. And again, for realistic galaxies, this is the typical realistic range of Bondi radius. So when we plot different simulations with different Bondi radius, all of these different dots represent the time average accretion rates from simulations with different Bondi radii. And we have found that for larger values of Bondi radius, we find a stronger suppression of accretion with respect to the Bondi rates. And the dependence on the Bondi radius, it goes as RB to the minus half. So we were able to extract the subgrid prescription for accretion like this. For feedback efficiency, we have looked at the feedback efficiency, which is a dimensionless parameter quantifying how much of the accreted resonance energy gets converted into the feedback power E dot here. When we looked at the feedback efficiency as a function of Bondi radius again, or equivalently as a function of the temperature, the ambient gas temperature. For a spin of 0, shown as green dots, we find that the feedback efficiency is around 1 to 2%, regardless of the Bondi radius. And we claim that this is the baseline level of black hole feedback, because when we add black hole spin, it's only going to increase from here. When we simulated the same set of simulations for black hole spin of 0.9, shown as black dots, we found that the efficiency is around 30%, And we have also, I will also note that these are very different from typical small scale GRMHD simulations, where we typically find efficiency greater than 1 for prograde simulations. Please ask me if you're interested about what's different in our large scale simulations. Importantly, we find that these feedback efficiencies, as opposed to the accretion rate where it had a strong dependence on the Bondi radius, it was largely insensitive to the Bondi radius. And also I will note that they are insensitive to the initial angular momentum. Now, this is the full compilation of all the feedback efficiency for all our for the complete suite of simulations as a function of Bondi radius and black hole spins shown as different colors. And here I'm showing the accretion rate and feedback power in units of the Bondi accretion rates as functions of the Bondi radius and black hole spin again. From these information in this paper this year, we now provide simple analytical fits to these data as functions of Bondi radius and black hole spin, which can be directly used in cosmological simulations or semi-analytical models as subgrid prescriptions for accretion and feedback. This will be particularly useful because these are spin-dependent quantities, where this will be particularly important, useful for simulations which track the black hole spin, such as New Horizon, Calibre, Arepo, or Open Gadget B. Not only do we provide the time average quantities of accretion and feedback, but in this paper, we also provide the distributions of accretion rate and feedback efficiency to fully represent the large variability in our simulations. We also provide the rate of change in the black hole spin for these subgrid models to self-consistently track the black hole spin evolutions. And we find that all our simulations find spin down of the black hole spin. However, that spin down timescale is almost comparable to the Hubble timescale, which indicates that these sub-Eddington accretion flows that we're considering here, the black hole spin basically is frozen at that value during these phases and can only evolve in maybe thin disk states or super Eddington accretion states. Coming back to this sad separation between black hole scales and galactic scales, with the multizone method, we are now able to extend the reliable radial range of GRMHD simulations and fully bridge the black hole and galactic scales for the first time. By achieving this quasi-steady equilibrium from horizon to galactic scales with this method, we can directly read off the feedback informations that's coming out from the scales that are covered by galaxy simulations and can provide spin-dependent black hole subgrid models from first principles without any free parameters. In the future, we would like to use these simulations to compare against observations. Here I'm showing our simulation, zoom out of our simulations on the left and observation of M87 jet on the right, observed at multiple different scales. As opposed to previous simulations where they only had access to only black hole scales or only galactic scales, we now for the first time have the full dynamic range of this jet from all the way from the black hole event horizon to galactic scales. And in my opinion, this offers a very unique opportunity in testing our theoretical understanding of black hole accretion and feedback against observations, and also a new opportunity to discover new physics. So that's it, and thank you very much.